Hi, everybody. So now I want to talk a little bit about continuous functions. This is just sort of like our first pass through the subject. And again, I'm rephrasing this, kind of redoing the order of the textbook, because when we do things like the product topology and the subspace topology, I think there's a slightly better way than the book presents to introduce it. And it involves using continuous functions. So a continuous function between some topological space X and some topological space Y is going to be a continuous function. Oops. So it consists of a function between the sets X and Y that depends on the topologies of X and Y. So it is a function. I'll abbreviate the function with f apostrophe n. It's a function from X to Y such that for all subsets, say V in Y that are open, F inverse of V is an open set of X. So remember how we define, this is sometimes called the pre-image of V under F, or sometimes called the inverse image of V under F. I'll use those kind of like interchangeably. So this consists of all points, little x in... What the fuck? My pen is really acting up today. Such that f of x belongs to V. So something is continuous if the pre-image of an open set in Y is open in X. So it's kind of an interesting, small little exercise to check that it works on a basis. So I didn't really give a warm-up before, but maybe you haven't quite warmed up yet. Continuity can be checked on a basis. Or rather on bases, doesn't really matter. What does that mean? Well, part of that is I want you guys to kind of figure out how I would phrase that. So if we have, say, some basis of Y, and let's say V is a union of basis elements, let's say, I don't know, B sub J. Any open set can be written as a union of basis elements. Then F inverse of of V is equal to the union of all the F inverses of B sub J. So that, well, this is open if and only if all these are open. So in particular, the thing I want you guys to kind of do, just try on your own, is to make sure that this equality is actually true. This is true for any function, not necessarily a continuous one. All right, so this definition of continuity most likely doesn't sound like the one you might have seen before in like calculus or even analysis, which is essentially the same subject, but just kind of different levels of, rigor. The one you might be a little bit more familiar with is the epsilon delta definition of continuity. Say, example, I have a function from R to R, let's say with the standard topology on both. So you might have seen before, I'm assuming, that if something is continuous, it's continuous at every point of its domain. So I'm going to kind of use that fact shamelessly. So via the epsilon delta definition. What does that mean? Let's say a continuous at a point x naught. So we might have seen this, 1,000 years ago when you were in high school or middle school. I don't remember when you talk about continuous things. High school probably, pre-calc. You can say we draw x, we draw y. We can represent the graph of a function from R to R as some kind of like curve inside R2. So we have some x naught. And the function is continuous at x naught if you can draw its graph without lifting your pen off the page. Right? That's the idea. And we kind of refine that notion a little bit with the epsilon delta definition. So this is f of x naught. I must see to this pen. I think the nib is fucked or something. Who knows? So the epsilon delta definition refines this a little bit. You learn that if no matter what tolerance you give around f of x or f of x naught, I can find a small enough tolerance around x naught such that the image is contained inside the given tolerance. So maybe a little bit more precise. This looks like some epsilon ball around f of x naught. And this looks like some delta ball around x naught. So the usual definition goes like this, now with actual words, quantifiers, and everything. For all epsilon greater than 0, there exists a delta greater than 0, such that for all x in R with x minus x naught less than delta implies f of x minus f of x naught is less than epsilon. This is kind of just a formal way of rephrasing this picture I've drawn, that I can always find a small enough little blue delta ball around x naught such that its image is inside the given epsilon ball. Color coding. Like this. So why is this the same as what I've just done? Well, if I set v equal to my open interval around f of x naught, a radius, I guess, 2 epsilon, or radius epsilon, sorry. Radius epsilon, I can't think. Wow, my brain is just kind of garbage today. So this is a subset of R. So this is open, right? This is always open. Open in the standard topology because it's an open interval. And so if the function is continuous, it implies that f inverse of v is open. So what does f inverse of v look like at the point x naught? We know for sure that x naught must be in here because f of x naught is in v. So I want to check kind of the fact that this is open at the point x naught. So there exists, wish to show there exists some open neighborhood, open, such that x naught is in W, which is inside of F inverse of V. This would show it's open by that video we had before, that openness is local. But what does it mean for W to be an open subset? It means that I can check it on a basis. What on earth? What a weird pen, man. If you know why my pen is doing that, in Notability, Apple Pencil 2, make a post on Piazza or email me or something. It's kind of getting a little annoying. So I can check this on a basis. So that means I can find an open interval around x naught. It is contained inside F inverse of V. So there exists a delta greater than 0 such that this is true. But if that's true, that is exactly equivalent to this implication right here. And going the other direction, if I assumed the for all epsilon and everything, that is again just a kind of equivalent to checking continuity on a basis. Just to bring it in line with everything you might have seen before, or at least like the thing you might have seen before, most likely was continuous functions from R to R. All right. So another thing that I want you to check, you tell me why this is true. So there's a theorem. So I guess it'll just say the following are equivalent, TFAE. So if I don't specify the topologies, it's implied. So F from X to Y is continuous. If and only if, so I'll call this statement 1. For all X in U, already fucking up. For all X in X, and any neighborhood, so that is any open set that contains f of x, any neighborhood V of f of x in Y, U, which is F inverse of V, is a neighborhood of X. So it's an open set containing X. And moreover, F of U is a subset of F inverse of V. Sometimes this is called the neighborhood definition of continuity. So it's like looking locally in X instead of locally in Y. So I'm not going to ask you to prove that in general, obviously. Well, that's not obvious. But I want you to think about this in terms of the case of a function from R to R. So what does this say in terms of this example? What does that look like? Is it equivalent? Does the exact same statement? If this is the same thing as continuity, they must be equivalent. So I want you to draw a picture or prove something. All right.